Welcome back to this series on enriched category theory. Today we'll round off the basic definitions by introducing enriched natural transformations. Let's jump straight into the definition. For this we let S and T be V-functors from V categories A to B. Now, a V natural transformation, which I'll denote alpha going from S to T, is an Ab-A indexed family of components alpha A, which is a map in the monoidal category V from the monoidal unit to the Hom object between SA and TA. We can think of this component map as picking out some element of the Hom object between the images of A under S and the image of A under T. We can draw a diagram of this. So we have some object A in the V category A, and this is mapped under S to SA and under T to TA. And these are objects in the V category B. Now we have some Hom object between SA and TA. So this is B, SA, TA. And we can think of the component map as picking out some element of this Hom object. This family of components for every object in A is the data for a V natural transformation, and we need this data to satisfy some properties. Namely, we need one diagram to commute, which is the following. Okay, so a V natural transformation between two V-functors S and T is an Ab-A indexed family of components that satisfy the following commutative diagram. And this concludes the definition. Now, at first glance, this commutative diagram looks nothing like the usual naturality condition that we're used to, and the task is now to explain how this more complicated diagram actually reduces to the usual naturality condition in the case where we're enriching over set. For the following discussion, let's assume that V is actually set with a Cartesian product and the singleton set as a monoidal unit. And then we see that the components alpha A are actually maps from the singleton set into the Hom set of SA, TA. And what does such a component do? Well, it just picks out an element of that Hom set. So actually what we're getting is for each alpha A, we obtain a map SA to TA. So in this case, this is the same as for a normal natural transformation, because a normal natural transformation consists of a family of component morphisms, one for each object in the source category. Now we need these family of components to satisfy the naturality condition, which is if we're given some arrow f from A to B in the category A, then we need the following square to commute. So we can lift f under S to SF, which goes from SA to SB, or we could lift it under T to TF, going from TA to TB. And then we have on the top the component alpha at A, on the bottom the component alpha at B. I'm going to put bars above these because these are actually the image of the single object in the singleton set under a component alpha A. In any case, we want this square to commute, which in equation form is saying that TF after alpha A is equal to alpha B after SF. So this is the usual condition for a natural transformation for normal categories. Now, what does this have to do with this larger diagram which we're requiring for enriched natural transformations? Well, we can think of this square or this condition in the following way. We're given some morphism f between A and B, so that's an element of the Hom set of A and B. So in our diagram we start down here. We have f being an element of the Hom set between A and B. And from this arrow we generate this square where we require that the two directions in the square be equal. That is, for each arrow we have such a square and we need the square to commute. And this idea is precisely what the diagram on the bottom is doing. So we use first, if we go along the top path, the inverse of the left associator to get from F to the singleton. So it's a pair of the singleton and F. And this is just so that we can then, with alpha B tensor S, pick out the component alpha B bar, comma SF. So we have this pair of the component of the natural transformation and the morphism F lifted under S. And then we compose with a composition map to get alpha B after SF. So this top path takes some arrow in our category, so that's an element of the Hom set between A and B, and gives the composite alpha B after SF. Now the bottom path does something similar, so we take F under the inverse of the right associator to F comma star, and then map that to TF and alpha A, and then we compose to get TF after alpha A. And the commutativity of this diagram is saying that both of these composites are equal. So in fact, in the case where V is set, the definition reduces to our usual notion of a natural transformation. And hopefully this also gives us a general intuition for why this condition makes sense for a general V category. Before moving on to an example, let's observe that based on these components alpha A we're given, we can actually compose two natural transformations if their codomain and domain are compatible. So suppose we have a V natural transformation between functors S and T, and another one, beta, between T and U. Now we're curious about what the component of the composite natural transformation at some element A should be. And this is given by the following composite of maps. We have that the monoidal unit is naturally isomorphic to being tensored with itself. And now we apply beta at A tensored with alpha at A. So these are the two components of the respective natural transformations, and we get, so this is a map into TA and UA tensored SATA, and now these have matching codomains and domains, so we can actually compose in the category B using the composition map to get some hom object SA and UA. So this is actually now a map. If we look at the entire composite of these maps, this is a map from the monoidal unit to the hom object between SA and UA, which is exactly what we need for a component of a natural transformation between S and U. Okay, so we've seen how to define enriched natural transformations, and we've seen that in the case where V is set, we get back our usual definition of a natural transformation, and moreover we can compose two natural transformations vertically. With that, let's turn to an example. We let R be a one-object Ab category, and we let M from R to the category of abelian groups and N from R to the category of abelian groups be Ab-functors. Now we saw in the previous videos that a one-object Ab category is just a ring, and in the last video we saw that Ab-functors between a ring and the category of abelian groups considered as an Ab category corresponds to a left R module. So M and N are left R modules. And for convenience, we'll denote the image of the single object under M simply as M, and the image of the single object under N simply as N. Let's now consider an Ab natural transformation, which we'll call capital H from M to N. By definition, we know that such an Ab natural transformation consists of an Ob-R indexed family of morphisms, but R just has a single object, so in fact we just have a single component, which I'll denote H star, which is a map from the monoidal unit in Ab, which is the integers, to the hom set of M and N in Ab. This is because this is just M of star and this is N of star. Moreover, this map, or this single component, is required to satisfy the V-naturality condition, which I'll write down. Okay, so let's think about what this means. We first observe that this H star is a map in the category of abelian groups, so this is a group homomorphism. Moreover, this group homomorphism is determined by where it maps 1 in the integers, so we'll call this special element H. Now, the commutative diagram on the bottom is saying that if we take some A in the ring R and then chase it around the diagram, so the top path maps A to 1 tensor A. Next, 1 tensor A is mapped under H tensor M to small h tensor MA, which composes to H after MA. Taking the bottom path, we map A to A tensor 1, which is mapped to NA tensor small h, which is then mapped to NA after h. and these two maps are supposed to be equal. Let's see what we have here. Well, H is a map from M to N, while MA is an endomorphism on M, and NA is an endomorphism on N. Now let X be some element of M, and recall that we interpreted the endomorphism MA as scalar multiplication on the left by A. So what this equation here is saying is that H after MA of X, which is just equal by our interpretation to H after A times X, should be equal to NA after H of X, which is equal to A times H of X. So we can rewrite this after up top as just mapping A times X under H. Therefore, the commutativity of the diagram for the V naturality is giving us this condition, which is just the fact that the map H needs to be R linear. This is just this condition that we wrote down is compatibility with the scalar multiplication with elements of R, and the fact that H is an element of the Hom set between M and N in the category of abelian groups means that H itself is actually also a group homomorphism. And so, in fact, we also have that H of X plus Y is equal to H of X plus H of Y, completing the requirements for a R-module homomorphism. Thus, we've seen that if we think of Ab-functors between a one-object Ab category and the category of abelian groups enriched over itself, if we think of that as being left R modules, then an Ab natural transformation between two such left R modules is actually just an R module homomorphism. Thus, once again, we've managed to recover a notion that we've known before from a special case of enrichment. If you want some additional examples, you can work out what Boole natural transformations between two Boole functors are and what cost natural transformations between cost functors are. However, in that case, it turns out because the original cost categories and Boole categories aren't very structure rich, that the notion of the corresponding natural transformation isn't very interesting. With that, I'll conclude today's video, and I hope that this series has given you some insight into how one can do category theory in the more general setting of enriched categories.